Hello and welcome to this video. We are going to take a look at exercise 6.4.3 from the book Analysis 1 from Tau. And it's quite a huge exercise compared to others. Maybe at the first glance, we still have to prove 4 remaining parts. A and B are already proven in the book. But they are all relatively easy to prove with part A and B of the proposition. And I wrote them down here for the case with the supremum, but in a quite different form. Instead of writing for all x greater than L, I write for all epsilon greater than 0. That has the advantage that we can write L plus in the definition, and this will be useful. And we start with part C. And for that we will use part A of the proposition for this case that L minus is smaller or equal than L plus. But at first we will take a look at this case here. The case with the infimum is proven similar. So we want to prove that L plus is smaller or equal than the supremum of the sequence A starting at M. And for that we are just going to write down the definition of L plus. L plus is just the infimum of the sequence AN plus starting at M going to infinity. And this supremum is actually just a part of the sequence. And if we take the infimum of the sequence, then of course a part of the sequence will be greater than the infimum. So this should be clear just by the definition. So we take a look at the middle case. And for that we will use part A of the proposition, how I already told. And we will just write down what we got. We know from A that for all epsilon greater than 0, there exists an 1 greater than M such that for all n greater than n1, an is smaller than L plus epsilon. And we are doing the same with the infimum. For all epsilon greater than 0 exists an n2 such that for all n greater than n2, an is greater than L minus epsilon. And now we can see why the different form of proposition or A and B are useful. We have L plus, L minus, and we have an in both cases. And now we can just put them together and form a useful inequality. At first we need to define n as the maximum of n1 and n2, and then it follows that for all, now we are just writing down like this. Now it follows that an is smaller than L plus epsilon, and an is greater than L minus epsilon for all n greater than n, and as n is just the maximum we defined right here. And now we just put them together. From here we can see that L minus epsilon is smaller than an, and an is smaller than L plus epsilon. And if we add epsilon on all sides, we get that L minus is smaller than L plus 2 epsilon. Okay. And from this follows that L minus is smaller or equal than L plus. We can't actually deduce that L minus is absolutely smaller than L plus. You can think of it just in the case that L minus is equal to L plus. This inequality still holds. Take a note that this is true for all epsilon greater than 0. So we can't actually deduce that this is absolutely smaller, but it is smaller or equal than, and this is exactly what the proposition wants from us to prove. Okay, let us see. Now we are going to prove D. And D is pretty similar. We want to show that if the sequence A is converging to some real number C, then L plus is greater or equal than C. And one thing again to see, take also in mind that L minus and L plus are extended real numbers. So this also holds if L minus or L plus are infinity or minus infinity or something like that, because A and B are proven for extended real numbers. Yeah, that's just one thing to add here. We don't need to consider any special cases. Okay, back to D. We want to prove if the sequence A is converging to C, then L plus is greater or equal than C. Again, we will just take a look at the right case. The left case is proven similar. And for that, we will just write down two definitions. The one definitions we get from proposition A, and the another definition we get from proposition from the proposition we get from the definition of convergence. Okay. So at first we know from A that for all epsilon greater than 0 there exists n1 greater than m, such that for all n greater than n1 an is smaller than L plus epsilon. And we know from definition of convergence that for all epsilon greater than 0 there exists n2 greater than m, such that for all n greater than n2 an minus epsilon is smaller than c is smaller than an plus epsilon. And yes, this is because an lies in the epsilon field, don't know if it's the correct term, of C. It simply follows also from this statement. You will also see more often in the book. And we can just combine again, like we did in C. So from this follows, if we choose again the maximum, of course, that C is smaller than an plus epsilon is smaller than L plus plus epsilon. So it follows that C is smaller than L plus epsilon. That again holds for all epsilon greater than 0. And from this, it follows again that C is smaller or equal than L plus. Okay. Yeah, very similar to C. Okay, now we are going to prove E. If L plus is a real number, then it is a limit point of the sequence AN. We will just take back in mind what we need to prove, that L plus is a limit point of the sequence. We just need to find for every epsilon greater than 0 some index such that AN lies in the epsilon field of L plus. Yeah, and for that will be B useful, but also A. So now we are just going to write down what we know from A and B. But I will do it a little bit shorter. So from A we know AN is smaller than L plus epsilon. And from B we know, but I don't will write it shorter because we have different quantifiers on the different quantifiers, but in different order. We know that for all epsilon greater than 0 and for all n greater than m, there exists an n greater than n such that AN is greater than L plus minus epsilon. Okay. And if we take a look at the quantifiers, you can just look over here. We can see that A is just stronger than B. So we will use the same quantifiers as in B to combine these two. So for example, if this holds for n greater than n1, we will put n1 into here. Oops. And then we know there exists an n greater than n1 such that this holds, and we know for that n also this holds what we know from A, because A is stronger. Okay, so we can just combine these two again. We just know it works for one n, both of these cases. So we know that AN minus epsilon is smaller than L plus because of A. And we know that L plus is smaller than AN plus epsilon. We know this from B. And of course, that's just the same as AN minus epsilon is smaller than L plus is smaller than an plus epsilon. And this just means that an lies in the epsilon field of L plus. So we have also proven this. And yes, be careful with the quantifiers. We only know that this holds for every epsilon greater than 0. There exists this n, but it's not for all n greater than any index. If that will be the case, this sequence will be converging to L plus, but that's not the case. L plus is only a limit point. Okay, that was part E. Now we will prove F, the last part. And we will using only A for this. But I mean, we have two parts to consider. We have this equivalent sign here. The left to the right follows immediately of proposition 6.4.5 that just says if the sequence is converging to some real number C, then C is the only limit point of the sequence. Okay, so we only need to prove the backward part. So if L minus and L plus are both real numbers and equal, then the sequence is actually converging to L minus or L plus. Okay, so this part is clear by proposition 6.4.5, and we only need to take a look at this. Okay, and we will again just write down what we know from A. And now take in mind that L plus and L minus are equal. That means we can apply A for the infimum and supremum part equally for the same number, C. And then it just follows that an is greater than C minus epsilon, and an is smaller than C plus epsilon. And you can see, similar to E, it just follows that an minus epsilon is smaller than C is smaller than an plus epsilon. But again, careful with the quantifiers. In this case, it actually holds for all epsilon greater than 0 and for all n greater than some n. And this n is again just the maximum. Yeah. That is the full proposition, 6.4.12. If you have any questions, feel free to ask, and then I will say goodbye.